Okay, we are going to take a look at this next section called explaining acids and bases. So essentially, when we talk about acids and bases, so far we've talked about Arrhenius' theory with the fact that acids will ionize and form hydrogen ions and water, hydrogen ions and a negative ion in water, and a base will form hydroxide ions in water. So we know that these two principles are pretty widely accepted, and we've briefly talked about how we now know that our hydrogen ions are so attracted to the water molecules that they actually form a hydronium ion, which is what we use to calculate our pH. So we want to look a little bit about revising Arrhenius' theory because we know that there's certain entities that have acidic or basic properties that don't immediately dissociate into either hydroxide, for example, or hydronium ions. So we'll take a look at what this means. So we have two key ideas. We have collisions of dissolved particles with water, and our water molecules. And we have the nature of the hydrogen ion, again, which is so attractive to these water molecules that we have this hydronium ion being formed. So initially, we have substances that are acids that react with water to form these hydronium ions. Again, these are H3O ions. So in our example, with our hydrochloric acid and our water creates H3O and chloride ions. So again, we have this negative ion being formed, and we also have our hydronium ion being formed. So this is now what we know acids to be. However, what about something like sodium hydrogen sulfate? It also has some acidic properties. So, because it's an ionic compound, we know that this ionic compound will first dissociate into its two constituent ions, sodium ions and hydrogen sulfate ions. So, we have Na positive and HSO4. Well, what will happen following that is that there will undergo a secondary reaction where we have HSO4, where it appears that this could still sort of dissociate, and we have this hydrogen ion then being dissociated and being able to readily react with our water molecule. So what we see is this hydrogen ion reacts with this water molecule, forming hydronium, and the remaining ion that gets left behind, well, if we look at charge balancing this, we have 1H positive and SO4 2 minus with a net negative charge of -1. So when we do that, if we lose one more positive charge, we get a resulting charge of -2. So we get our hydronium ions and a sulfate ion. So we see that we can still have acidic properties even if we don't have an initial reaction of this hydrogen with our water. It's a secondary reaction. So we have first dissociation of our ionic compound, and then we have ionization of our acid reacting with our water to form hydronium and sulfate. So we've had to modify Arrhenius' theory to say that acids have properties that still form hydronium ions, but this can be through a variety or multiple steps. Now, bases generally, we say, are substances that react to form hydroxide ions, and that remains consistent, but we are used to seeing examples where there's hydroxide ions as a primary product. So in this example, we have calcium hydroxide forming calcium ions, and I should have a 2 there, 2 hydroxide ions. So we have calcium hydroxide. Again, this is what we would expect, and this is what we've seen with bases. However, again, we have some examples. We know that we have substances like sodium hydroxide where we have NaOH forming our sodium ions and our hydroxide ions. We do expect that to still be basic. Okay, we also see examples like ammonia. We know ammonia is very basic as well. And in this case, we have this guy reacting with water to form, and actually I should put that in there, we react with water, and what happens is because this is a base, we still get the formation of hydroxide ions. Okay, and that hydroxide ion actually came from water, but because this is technically, now I'm gonna do this right now, and I'm gonna show you why. H2O is the same as HOH, and this just helps me see that I have a hydroxide ion here and a hydrogen ion here, and that way I can see where my ions are moving around a little bit better. So I have this hydroxide ion, which means that this hydrogen ion had to join up with this guy. Okay, so what happens here is I get my hydroxide ion plus NH4. Well, because I've gained a hydrogen ion and each hydrogen ion has a positive charge, that results in a 1 positive. So I have this ammonium ion. Well, what about our example with our sodium carbonate? Let's take a look at what happens here. Well, first we have dissociation of sodium carbonate. So we have Na positive, there's 2 of them, and we have carbonate, CO3, 2 minus. So that was our first reaction. Now, the basic component of our sodium carbonate isn't sodium, it's this carbonate. So then, in our secondary reaction, we have carbonate reacting with water to form, well, we know that this is a basic property, so it's going to form hydroxide ions. Again, that hydroxide ion comes from our water molecule, okay? And we get this remaining hydrogen ion to react with the carbonate. So we get hydrogen carbonate, HCO3 minus. So how do we know how to predict these types of reactions and what is really going on here? So let's take a look at that. So to start out, we write the chemical formula of our reactants with the molecule or polyatomic ion plus water. So if we have an acidic property, or we have an acidic solution, we're going to be forming our hydronium ion. If we have a basic property, we are going to form the hydroxide ion. Okay, we complete the other products by determining the combination of atoms and charge required to balance the chemical equation. So one thing you need to keep in mind is that when we form a basic solution, we're forming this hydroxide from our water molecule. When we form this hydronium ion, we form that from our water molecule. So what we say is that if we have an acid is what we call a proton donor. So it will give up a hydrogen, okay? And when we talk about protons, we're talking about hydrogens. So it gives a hydrogen, okay? When we talk about bases are proton acceptors. So they take or receive hydrogens. So that will help you jot out these reactions. Now, if we jump back, let me just slide back to our other slide here. If we take a look at that definition now and apply that to how I've derived these formulas, we can see that in our ammonia, we know that it turns red litmus paper blue, so we know that this has basic properties. So we do expect hydroxide to be formed when we react it with water. Now, because this doesn't readily react to form hydroxide, like our dissociation of sodium hydroxide, we expect there to be hydroxide here. So because of that, our ammonia is our proton acceptor, or it accepts hydrogens from another entity. This is why this hydrogen here will transfer over to this ammonia, because ammonia is our proton acceptor. So when we look at these two entities here, sodium and carbonate, well, because protons or hydrogen ions have a positive charge, sodium won't want to take any more hydrogen ions. Also, that would be hydrogen with a positive charge and sodium with a positive charge. Two positives don't really like to be together. And it would form sort of a metal compound, because we'll have two sort of metallic properties together. However, when we look at this carbonate, we see that it has a 2 negative charge, which means that it kind of is okay with accepting another positive charge or another proton, or in other words, it's okay with accepting some hydrogens. So because it has a negative charge, it's willing to accept the positive charges of our hydrogens from our water molecule. So what happens is this becomes our proton acceptor, and this hydrogen again gets transferred over to our proton acceptor or our hydrogen acceptor. This guy takes our hydrogens, forming hydrogen carbonate. So now that we know that, we can form these equations. However, one thing we also need to note is that whenever we balance these equations, we need to have what we call mass and charge balance. So we need to balance mass and charge. Has to be balanced. So what I mean by that is if we look at our products and our reactants in our chemical equation, we see that we have 1 nitrogen, we have 5 hydrogens, and 1 oxygen on our reactant side of this ammonia reaction. When I check over here, 1 nitrogen, 5 hydrogens, and 1 oxygen. So that has balanced our mass. Okay, in other words, when we talk about balancing mass, it's just balancing the number of atoms. Okay, so number of atoms on both sides. When we talk about charge being balanced, we want to make sure that there's the same number of positives and negatives on both sides of the reaction. So on our reactant side, we see that there's a net charge of 0. On this side, we have a 1 negative charge, and we have a 1 positive charge. Well, the 1 negative and the 1 positive give us a net charge of 0. So we've actually also balanced our charge. If we look at our next equation here, we'll look at just the pink one. This is also balanced technically. If I look at my sodium carbonate, I have a net charge of 0. And if I look at 2 times my positive 1, which is positive 2, and I have 1 times my negative 2, which is negative 2, so this is also a net charge of 0. When I take a look at my pink example at the bottom, I have 1 carbon, 1 carbon, I have 4 oxygens, I have 4 oxygens, I have 2 hydrogens, and I have 2 hydrogens. My net charge on this side is equal to, it looks like I have a positive 2 here and a 0 here, so overall for my entire reactants, I have a positive 2 charge. Okay, so when I go to, and when I say positive 2, this is just because I made a mistake here. This is not positive 2. Oopsies. Let me just erase this. This is actually negative 2. I'm not sure what I was doing there. Negative 2, negative 2, and this is also a negative 2. So, sorry, negative charge, our charge, a net charge of negative 2, okay, our carbonate, net charge of negative 2. Now, if we go on to our product side, we have 1 hydroxide with a negative charge and 1 hydrogen carbonate with a negative charge. Again, our net charge on this side is negative 2. So our net charge is identical on both sides. Now, it doesn't matter that it's not 0, it just matters that they are equal, a negative 2 and a negative 2 on both sides, therefore balancing our charge. So this is why we have to come back and we have to make sure our atoms and charge is balanced, okay, in the chemical equation. So this is how we would write out these modified Arrhenius theory. Now, what about when we talk about a neutralization reaction? Generally, when we talk about neutralization reactions, we were talking about the reaction of hydrogen plus hydroxide forming water, or HOH or H2O, whichever you prefer. So when we have hydrogen hydroxide forming our water molecules, that's what we know so far. However, with our modified Arrhenius theory, what we see is that our hydrochloric acid actually dissociates into H positive. Oh, well, let me just see here. Dissociates into H3O because it reacts with water. So we have H3O positive. Because there's so much water available, because these have to be dissolved in water to react, we have lots of water available. So we have H3O plus our Cl minus. Okay, now we also have our sodium hydroxide. So we have our sodium and our hydroxide. So what happens is our two positive ions are sort of going to play in a double replacement reaction and switch spots, and we get H3O reacting with OH, forming two water molecules, or two HOHs. Okay, sodium chloride will also react to form NaCl, so I'm just going to put that in brackets. NaCl is also formed, and it's aqueous in water because we have lots of water surrounding it. So now, instead of identifying a double replacement reaction for neutralization like the top way here with our hydrogen and our hydronium, our hydrogen and our hydroxide, we actually have it like this, our hydronium and our hydroxide forming our water molecules. So this is sort of the new ways of thinking about acids and bases in terms of modified Arrhenius' theory and changing sort of what we know about our acids and bases. So at any point, if you need to go back and rewind and take some notes, please do so now, and good luck.